which is what creates our negative pole and our positive pole. But if it's so strong that it just rips it completely away, it's not a polar covalent anymore now, it's just ionic. So here's a table of a few bonds, doing the math for you. Non-polar covalent, polar covalent versus ionic. But it's all just using those benchmarks that they gave you in that earlier slide, right? Basic math. Which category does it fall into? All right, shapes. Yeah, technically I've got 15 minutes, right? 8:55. Let's see if we can get through shapes. All right, remember before we had that space fill with the ball, with the thing down, with all 4 little white dots, right? So, here's our Lewis structure for that methane. It has a tetrahedral structure where every hydrogen is separated by a bond angle of 109 degrees. We can actually get a little bit further than that if we wanted to. It's fairly specific, but 109 is close enough. 109 degrees between every hydrogen surrounding that carbon. All X, Y, 4 bonds, where we're dealing with single bonds, are going to form that tetrahedral shape. Everybody follow? X, Y, 4. If it's single bonds, X, Y, 4, where it's all bond. Now, here's the reason why I say if it's single bonds. X, Y, 4. That works if it's this. Right? But you could also get this. That would also be XY4. Right? There's one X and 4 Ys. That would not be tetrahedral.
Wait, is that a Y or a 4 that you wrote below that X on the middle one? No, that. Is that a Y? Okay.
Yeah, they almost look like sigmas, don't they? Because I'm doing it fast. These shapes only work if we're talking about shapes around a central atom. Alright? So when we're talking about the shape of these molecules for this chapter, we're not going to get into something like this, where it's all sorts of hokey weird. Every other shape is going to be a variation of this, though. But it's not going to look like that, but I want you to appreciate that it is that. It's just missing one end. So the goal for this section is learn to predict the three-dimensional structure of a molecule. What shape is it going to be? And this leads us to the super valence shell electron pair repulsion theory. That's a really long name and a really hard to remember acronym. Hard to remember a word that we use to abbreviate something. And pretty much all it says is the reason why these things spread out is because those electrons in that valence shell, they are all negatively charged. They want to spread out so that they are as far away from each other as possible. Thing is, those pairs have to stick together because they're involved in covalent bonds. So the pairs stick together. But that means that those 4 pairs want to be as far apart from each other as possible. And in a sphere, that means that they will be 109 degrees away from each other every time. Unless, of course, you start adding in double bonds. If we add in double bonds, that means 2 pairs have to be close to each other, right? Because they're in a double bond. So now what's our bond angle between those 2 oxygens? 180 degrees, perfect line. Because, why? These guys right here are locked in place because of the double bond. So what's it going to do to everything else? Push it as far away as possible. And when you're dealing with electrons on both ends, That means that it's all the way out there, spread out like you're trying to spread eagle or spread your arms as far as you can. Linear. So, if we are dealing with double bonds, the shape of the molecule with respect to that double bond is going to be linear. The carbon and the oxygen in this case are directly apart from each other. Straight line, linear. And the other oxygen is all the way on the other side. Can you take this lesson and apply it a little bit further? Remember that HCCH, C triple bond CH? What's the, I mean, I kind of showed you when I drew it, but what's the shape of that molecule? Triple bonds are even more rigid than double bonds. So what do you think the shape of that molecule is going to be? All that negativity on one side, what's going to happen to the hydrogen? Is it going to be off like at an angle? It's going to be as far away from all that negativity as possible, right? Which means it's just going to be a straight line. Just like this. All right. If we add a double bond and two single bonds, instead of 109, what's happening? We have 120. And this is planar. Why? Those two pairs have to stay right there, right? But that means that the electronegativity around this bond right here and around that bond right there, both of them need to be pushed as far away from everything as possible. So why wouldn't it be up here? Because that would put it too close to this guy, right? To all of this stuff right there. So it's going to be shoved down. And if it gets anywhere, like this is on the plane of the board right here. Everybody follow? If this guy right here pulls a little bit out in front of the board, it's getting too close. It's putting too much pressure. It's getting too close to some of that other negativity. If it goes behind the board, it's getting too close to that negativity. And it's certainly not going to pull up like this, right? Or it's not going to go down like that. We're not going to pinch these two guys together because now they're too close to each other, right? It's not going to do this. Because there's negativity here and negativity here. Just like there's a lot of negativity there. The electron repulsion theory is what is used to describe why these small, simple molecules take the shape that they do. It's all because of that negative, the repulsion, the negative repulsion of those electrons. So, why is this sulfur dioxide molecule also planar? With that same 120-degree angle. It has a lone pair right here, right? And that lone pair has the same electron density as that right there. Because that line is just a pair of electrons, right? So if we looked at this as pairs of electrons, we have a double pair here and two single pair. It's exactly like this. A double pair here and two single pair. So this has the same shape, it's just missing that third guy. It's an invisible guy because it's just the electron pair right there. Everything is about getting that electron density as far away from each other as possible. So what's the shape of our CH4? Tetrahedral. 109 degrees. Now, I want you to appreciate something. If I take these two little white balls right here, and I force them to squeeze together, that is going to bring a lot of electron density right there. But what does that also mean about this 109-degree angle right here?
Spread out.
They have room to spread out, right? Because I just took these two guys right here and squeezed them together. I moved them closer to each other. By pinching those two white balls, these two guys can spread out from 109 to 120. Because that's what a double bond is. It's forcing those two bonds right there closer together.
Thank you.
For the sound effect? Or for
No, you want us to appreciate it, and I did.
Oh, okay. Sure. Trigonal pyramid versus tetrahedral. What's the difference? What's missing in that trigonal pyramid? That top ball up there, right? But it's not because it's not there. The electron density is still there. It's just invisible. It's that lone pair on that nitrogen, right?
The eye of horns.
Sorry, don't see it.
Top of a dollar bill.
Oh, yes, okay.
The Illuminati thing?
Yes, the Illuminati, yes. I apologize. Totally different thing, but yes, that's what he was talking about. What's the bond angle between those guys going to be? It tells you up here, but even if you didn't look at it, you'd be able to tell me, right? You should know. 109, because it's the same thing as the tetrahedral. It's just that that top ball is invisible, right? But the electron density is the same, and so the bond angle is going to be the same, right? So why does water look the way it does? This is that same tetrahedral shape. Except instead of one invisible ball, now we have two. What's that bond angle going to be between those two hydrogens? It tells you on the slide, but you should know it. 109. Everything is bent 109. As everything's single bonds or lone pairs, it's always 109. The only thing that changes that is when we start adding in double bonds and triple bonds. Then things can bend as far out as 180, right? A triple bond, that puts you at 180. Or two double bonds on either side, that's 182.
And only when it's single bent, it's 109. Like bent shape, 109. Bent wedge stash, 109. But
Yeah. All of the angles, like the angle between these two hydrogens is 109. The angle between that hydrogen right here
yeah.
and the pair up here is also 109.
Oh, that's gonna be.
Everything is 109.
What's the 120 thing?
The 120, well, everything in the tetrahedral is 109. The 120 happens when we get the double bond. We take two of those things and we bend them closer than 109.
Oh,
Okay.
And that gives the other guys room to spread out to 120.
And that's only if it is.
That's only if there is a double bond.
Okay.
And two single bonds.
The double bond is always gonna be like 120.
A double bond will give you a 120-degree angle between all of the bonds.
Okay.
but then two single bonds is 120 as well, right?
Two single bond with a double bond out, yeah, it's 120.
Always 120?
Well, here's the thing. What's 120 times 3? 360.
So not always.
Because it's a planar circle, right? So the bond angle between those two single bonds is 120. And the bond angle between any single bond and the double bond is 120.
So it's not 120.
Right. Because literally those two bonds, it's not even that they're squeezed next to each other, they are literally on top of each other.
But to count the whole would be like 360 if it were.
Right. But the only reason it works that way, because if you 109 times 4 is not 360,
No.
but that's because we're not talking about a plane anymore, now we're talking about a sphere. And so you have to draw a plane, which is why you have 4 planes here.
Okay.
The 4 sides.
So whenever it's
This-
109, we're always dealing with a plane. Is that what you're saying?
When there's a double bond, everything is on the same plane.
Okay.
When it's a single bond, you are talking about the plane in between two angles, but every bond is going to be on a different plane with respect to another bond.
Okay.
It works like this. If you take your 2 fingers, spread out your fingers as much as you can, and then shove them together in a really inappropriate gesture.
Why are you doing that?
Because that's the bond angle.
Okay.
2 of them are going to go up and down, up above the plane and down below the plane, and 2 of them will be right on the plane.
But we're not going to forget that.
Not going to forget that metaphor, are ya? I didn't tell you what inappropriate gesture it was. You filled in that detail. I just kind of like showed you where the gutter was and let you jump in. Anyway, are we?
Yes, we're done.
Okay, electron group. So yeah, that's pretty much talking about the same thing.
Good way to end.
Prediction, and then we're there. Alright, good. So, we're not going to finish this. So, that means that this test will not have chapter 6.
Oh, there's only.
I'm scared of that.
Or do you want to finish?
No.
No?
No.
I
Let me
think
just-
you should put it on the test.
Can we just tell you to put it on the test and whether it gets out?
What are we at? How many's left?
Just like
Three slides? 4, 5, 6, 7.
15.
On dipole, yeah, that's quite a, that's
It's just 6.9.
just 6.9, but that's quite a
Just
bit.
put it on the test.
Put everything at 6.9.
It'll be fine.
No, see, that's not what I'm doing. I'm not gonna put everything but 6.9. Not gonna do
Just
that.
put it on,
I don't
just
wanna
put it
put
all
it
on
on
the
the
test.
Important.
Just figure it out.
We will.
You should put it on. Good.
How about just leave chapter 6 off and we'll promise you that we learned it.
No. I'm willing to put chapter 6 on without finishing it if you all
Yeah.
agree to it.
Do it.
But,
You
yeah.
should do.
I like that.
Just put 4 hours.
Well, we had 2 people leave,
Okay,
so.
but if we take a vote and we all vote yes, then we outvoted them anyway.
Well, they're just not committed.
Can we take a vote?
Does everybody here say we want chapter 6?
Yes.
Yes.
Show of hands.
Get it over with.
We all,
I don't
chapter
want
6?
that.
Get it over with. I don't want to do
Oh,
it.
okay, awesome.
Or you can just stay here and teach it and he'll record it and then we'll watch
That works too, I guess.
it. Yeah.
Yeah, if you want to keep lecturing, I'll put it up.
No,
Yeah.
I'm okay with putting 6 on there.
Like you're
because
doing empty classes.
the likelihood that you'll get a question over chapter 6, over section 1, 6, 9 is low. But it is going to be your responsibility to know if I have it on the test. I'm not going to feel bad because everybody but 2 of you all are here.
I'm
You
willing,
just give us like 3 hours though?
I'm willing to take that risk.
One more hour? 2.5.
2.5 hours.
15 more minutes.
30 minutes.
Kelly.
We ain't winning that one.
That's
Remember how
okay.
community it was where
This is,
showed the
I have a
professor
4-year-old son and a
and a
9-year-old
couple of
daughter.
desks
This is
had
not hard. I can say
recorders.
no all day.
and then a few weeks later it was all recorders, and then a few weeks after that the professor had just left a player played all the recorders.
That was in a movie?
Yeah.
That sounds familiar, yes, where the whole class is just the professor playing and recording and all the students are recording the recording so that nobody ever goes to class. Yeah. Which, if I was really interested in doing it and had the backing, I could totally do. Just record myself teaching this class once, and then just post the videos every time, and then just let the computers do all the grading. And then all I would have to do is sit back and answer you guys' questions when you get confused about individual topics.
Do it.
Because that would make you feel great as a student, right?
Yes.
That's the flipped classroom model. It's beautiful.
So
Yeah,
it's
except
going
that there
on-
would
so
never be a flipped class in that
Chapter
situation.
6 is going on there,
Wait, what do you
correct?
mean?
Sure.
Oh, sure. Are you going over this now? Because I will stay.
Do it. Post
I
it.
could.
Because I'm here for it. I
I cannot force you to stay. But I can keep talking if you're still here.
I'll keep talking.
don't. Keep talking about it because I'm here for this. And I need to know this.
So the whole,
It's actually recording.
yeah, it's still going. They haven't like run out of space because I talked for 3 hours, 3 minutes.
Oh, the lens cap's on.
Oh.
I'm kidding, there's no lens cap.
All right, so the point of 6.9 is to figure out the polarity of a molecule. So, you should already be able to tell me, before you even get into this, water, is it polar or not?
Yes. Polar.
Why? There's 2 reasons why water is polar. One of them should be really obvious, and the other one should be really obvious for different reasons.
It's got those empty balls on top.
That's one reason. One side of that tetrahedral, right, is going to be nothing but negative electrons. There's no other positive charges on that side, right? And what's the other side? What's the reason why the other side, where the hydrogens are, why is that going to be polar too? Because what does oxygen do when it's sharing an electron with almost anything else?
Well,
It holds on to it really strong, right? Because it's very electronegative. So not only is one side going to be really negative because there's nothing but electrons, The oxygen itself, the center, is going to be pretty negative because it really holds on to electrons, and that leaves just those two hydrogens hanging out on the other side to give us a little bit of a positive, right? So water is polar, but the way we just answered that question is the whole point of 6.9, of appreciating what shape does. Where are the negative charges? Can we draw a line or point to a way in which this side is kind of positive and this side is kind of negative, and if we can, then it's polar. If we can't, then it's not. So, for example, this carbon right here and these chlorines. Chlorine is rather electronegative. Carbon is rather not. So where's most of the electron density going to be? Around those chlorines, right? But is it still evenly distributed everywhere? Is there a side of this molecule that is more negative than the other side? No, because all of these chlorines are pulling electrons away from that carbon equally, right? And in every direction. So is this a polar? Can we draw a side that's positive and a side that's negative? Nope. So this right here, the 4 carbon chlorine dipoles, because remember a dipole is any situation where we are creating poles, right? We do have an uneven attraction between the carbon and the chlorine, which does create a dipole. But there's 4 of them, equal, all pointing out in every direction, so not polar. There, 6.9 done. Just kidding. Is this molecule polar or not?
Which one?
This one right here, carbon dioxide. Carbon and oxygen. Oxygen is more electronegative than carbon, so it will create a dipole, right? Because anytime we have electronegative, an uneven electronegativity, it creates a dipole. Even if it's a tiny one, a little bit positive and a little bit negative.
I'm going to say no because it says CO2 is a non-polar molecule.
Yeah, exactly. You can cheat if you just read the slide. But the point is to think about it. We're creating a dipole here, right? But we are also creating a dipole of exactly the same intensity pointing in the opposite direction. So what's -4 plus +4? 0. What's -0.4 plus +0.4? 0. So this is also non-polar, because even though there is electronegativity between oxygen and carbon, they cancel out. Non-polar.
Does that last one be 0.0?
0.0?
-4, -0.4,
Negative 0.4 and positive 0.4?
Uh-huh.
Yeah, well, sure, yes. 0.0 for what we're worried about significant figures. Sure. So, what are we comparing here? We're comparing shapes. This is a linear molecule, right? This is a tetrahedral molecule, right? Now, could we change this molecule and make it into something that was polar? What would we need to do?
CO2?
Well, let's not mess with CO2, but we could do it there too. What would we do to this carbon tetrachloride to make it polar? Change one thing.
Put a hydrogen instead of chlorine?
Yeah, take that chlorine right there and make it hydrogen. Carbon is now more electronegative than hydrogen by a little bit. And so that means that that dipole right there, that arrow, is going to switch directions. And so now that hydrogen is going to be a little bit positive, right? And all these chlorines down here are going to be more than a little bit negative, right? Would that be polar? Yes. Because we have a positive end and a negative end.
Every time you say that, I'm thinking country and rock and roll.
Okay.
A little bit country, a little bit rock and roll.
Very good. Polar molecules, like hydrogen chloride, are polar because there is an uneven dipole. Anytime you're talking about a single bond, if there is a single dipole, if that electronegativity is different by more than 0.4, then it's polar. By definition, remember? Because how did we define whether or not we were dealing with something polar before? It was literally subtract the electronegativity values, and if it's 0.4 or less, it's non-polar. 0.4 to, what was it, 1.8 was polar covalent, and over 1.8 was ionic, right? So anytime you're talking about a single bond, if the electronegativity is more than 0.4, if the difference in electronegativity is more than 0.4, it's going to be polar. But the question is not whether or not this is polar, because that's easy to calculate. The question is a larger molecule polar? Like this tetrahedral molecule, is that polar? Well, in this particular case, carbon tetrachloride, no, it's not, because there are dipoles, there's 4 dipoles, but they're all pointed in directions and they cancel each other out. There is a dipole here with carbon dioxide, but they're pointed in opposite directions, so they cancel each other out. Water. We have a dipole that's pointing towards the oxygen, a dipole that's pointing towards the oxygen, and then just a whole bunch of negativity on this side over here. Could we draw a line, like right here, that we could then define as a negative side and a positive side? If we drew a line right there between the hydrogens and the oxygens, if the oxygen is keeping most of the negativity from those bonds, then that leaves these hydrogens as slightly positive, right? It leaves the oxygen as more than slightly negative, which means now we have a positive end down here and a negative end up here. These dipoles do not cancel out. They are in fact additive. They're both adding to the oxygen, and so therefore H2O is polar. Get a strong magnet and hold it up to a stream of water. It'll move. Because charged things respond to magnetic fields. Polar things respond to magnetic fields. Now, that's not to say that you'd be able to use a magnet test to determine whether or not a test question is polar. You'd actually have to do the math and think about the shape.
So it would be the water with the magnet, or would it be the things in the water?
The water with the magnet. Water
Okay,
itself.
water.
Pure water.
Okay.
Because water is polar. And therefore it has a positive and negative side. And things with positive and negative charges react to magnetic fields. That's outside the box for this chapter.
I just think about like the blow dryer and the water and how it's not necessarily the water, it's.
Right. No, that's a very different thing between conducting electricity, which pure water is bad at, but regular water with a whole bunch of crap in it is really good at, right? But that's a totally different thing from polarity of the molecule of water itself, which is what we're talking about here. So, this nitrogen, is that polar or not? Try to not read it. Tell me if you can answer it. Nitrogen with 3 bonds of hydrogen, so we have an ammonia. Hydrogen and nitrogen, are they significantly different with electronegativity? A little bit different. So yeah, we're going to have a dipole. We have that lone electron pair on one end that's going to be a nice placeholder for a whole bunch of electronegativity as well. Since all of these guys are pointing at the nitrogen, does that mean that this is polar? Yes. We could draw a line that says the nitrogen is very negative and the hydrogens are very positive, right? Or slightly positive at least, each. So therefore, it is polar. The dipoles do not cancel out, therefore it's polar. Oxygen fluoride, is it polar or non-polar? Oxygen difluoride, actually. So, how do we do this? Oxygen has an electronegativity of 3.5, fluorine has an electronegativity of 4.0. So the difference in electronegativity is 0.5. So is the individual bond polar?
Yes.
Yes, because it is more than 0.4, right? Which direction is it going? Where is the electron density going? Who has more?
What's the problem?
What's
Right.
more than 0.4?
The difference between oxygen and fluorine here, 3.5, 4.0 minus 3.5 is 0.5.
Oh, 0.4.
Or 4.0, 3.5.
I
The
had it
answer
in
is-
my head that it was it was bigger than 4, and I was like, how could that be?
Right, yes. So, the difference here is 0.5, which is therefore larger than 0.4, which is the cutoff for nonpolar, right? Up to 0.4, it's nonpolar.
Okay, so up to 0.4 it's not, but everything over 4.
0.5 to 1.8 is polar.
So,
Over that is ionic. Which means now we're not even talking about a covalent bond anymore, we're talking about, like, completely grabs them. Right? So, 0.5, the direct, yes, it is the electronegativity, the dipole is going towards fluorine because fluorine, oxygen is nasty, but fluorine is worse. So fluorine's actually pulling those electrons away from oxygen, which I'm sure pisses it off. But it can deal, because it's mean to everybody else most of the time. What's the shape of that going to be? We can draw the Lewis structure here, where we have this planar, triangular molecule, right? Where our dipoles are pointing away from the oxygen, both of them are pointing away. So is this polar or not? It is polar, because both of them are pointing away. They do not cancel out. Now, why is this a triangular molecule instead of linear? This is a question that refers you back to earlier things. Because there's no double bond. Fluorine, how many electrons does it need to share to fill up its shell? Just one. Which means it's not going to form a double bond with oxygen, it's going to form a single bond. Which means that those two pairs out there are by themselves. So it's not linear because there's no double bond. What's the bond angle between these two fluorines? Tell me.
109.
109. If there's no double bond, the bond angle is 109.
What? Sorry, I'm so zoned. Where is the 7th valence on the fluorine?
Fluorine has, well, here, it's in that line. That line represents two electrons, one from fluorine, one from oxygen.
Okay, got it. Thank you.
Good question. Ionic bonds are the strongest of the attractive forces found in compounds. Thus, most ionic bonds are solid at room temperature. Sodium chloride does not melt until 801 degrees Celsius.
Salt baths are nice.
Right, that's the irony, is that ionic bonds are incredibly strong as crystals, but they're incredibly weak in an aqueous solution. Because, tell me why. This is outside of the box. Tell me why.
Because water's polar and it breaks down the ionic bonds.
What is an ionic bond? It's an attraction between two opposite charges, right? Does water, being polar, have a positive charge that could attract the negative charge of chlorine? Yes. Does it have a negative charge that could attract the positive charge of sodium?
Yes.
Yes. So when you take a salt crystal that takes 101 degrees Celsius to melt, and you put it in room temp, like cold freaking water, 0 degrees, liquid water, what's going to happen to that salt crystal? Gone. Because water will rip it apart. Because there's a lot more water than there is salt.
And the irony is it lowers the boil point of water.
Yes. Which allows, it also changes the freezing point as well. So that would change the temperature at which it could be, so you could actually get water that's below the freezing point of water because it's salt water, which would still rip more salt apart.
Will it?
Yeah, up until you get to a point where you're saturated with salt, at which point it won't because there's no more room for entropy to take over and pay for it.
And it does it much more slowly, does it not?
All reactions would run slower, yes, but it would still do it. Alright, so dipole-dipole interactions. A dipole is simply where you take a polar, anything where there is an unequal electronegativity creates a dipole, right? Anything where that electronegativity is 0.5 to 1.8, it makes a dipole. A positive side and a negative side. We've talked about the attractions between those positives and negatives, right? So, dipole-dipole interactions are inter, very important difference. That's why I had to think about it for a second. Inter means between two different things, right? Intra means within the same thing. And you can still get intramolecular interactions from dipoles too. That's what all of proteins and nucleic acids are built on, but we'll get to that later. Intermolecular interactions. If you create this dipole between two hydrogen chloride molecules, which can't be in an aqueous solution because then they would have just, but forget about that for a second. So if you have this hydrogen chloride dipole, that negative chloride side is going to be attracted to the positive hydrogen side of another molecule. How strong is that attraction going to be?
Weak.
Kind of weak. Much weaker than the attraction between these two guys, right? But it's going to be there. And the stronger the dipole, the stronger that dipole-dipole attraction, right? Just like the stronger the magnet, the harder it is to get it off your fridge. I got some of those really super strong rare earth magnets. I love them. I put them on my fridge. One of the best reasons why I love them is because I have absolutely no fear that my son will accidentally swallow one. Because if you want to get those suckers off the fridge, you gotta really try.
Put them on a piece of paper and then fold the paper to the edge.
Don't break the fantasy! My son is not that smart.
They actually feed cattle magnets so that as they're grazing and they pick up bits of wire and nails.
Just to keep it in that one stomach so it doesn't go any deeper.
Right, and
Yeah.
so when they butcher, they take out the magnet, they clean it off, and they feed it to another cat.
That is That's hilarious.
So here's the thing. Dipole-dipole interaction is the attraction between the positive side of one dipole and the negative side of another dipole in another molecule. Or in a really distant part of the same one. But for our purposes with these really simple things, another molecule. There is a special type of dipole-dipole interaction, not because it is necessarily the strongest, but because it is the most ubiquitous, and that is called hydrogen bonds. A dipole interaction that involves a hydrogen ion as the positive side is a specific type of dipole interaction that gets a specific name called a hydrogen bond. And it is important because that dipole interaction, that guy, it's not that guy, that's unfair, that's between nitrogen, that guy! The dipole interaction between hydrogen and oxygen of other water molecules is the reason we are here today from a naturalistic standpoint. Because remember that weird thing that water does, where as it freezes, it gets less dense, and therefore it floats, thus protecting liquid water beneath it? The entire reason that happens is because of that hydrogen bond. That dipole-dipole interaction is strong enough to fight gravity. Have you guys ever seen the movie Bug's Life?
Mm-hmm.
There's a really neat thing in there where it's one of those like, ooh, I love it when animators actually understand science a little bit. There's a thing where they're like, he walks into the bar, right? And the barkeep's like, I'll have a drink, and so the barkeep gives him a water, but he doesn't give it to him in a glass. What does he do?
He's gonna drop.
He just goes, whoop, here, take this. And he's holding the drop in his hands like it's just a big ball of pizza, and when he wants some, he just sucks on it, right? Why doesn't the water just whoosh? Because if you tried to hold a ball of water that was appropriately the same size, it would not just whoop, sit in your hand like it's oh so nice. What would it do?
Surface tension.
Whoosh, surface tension. Strong enough to keep water skipper spiders, they can stand on water without getting wet. Because they're literally stepping on water and they're spreading out their weight far enough that the surface tension of water will hold them up. They don't get wet. What is surface tension? Hydrogen bonds. The surface tension of water is due entirely to the hydrogen bonding, the dipole-dipole interaction of different molecules of water. And it's everywhere in the water, everywhere, except for right at the top. All of those hydrogen bonds can only point to other water molecules, which means they're pointing to the side and they're pointing down, which makes the surface of water get just that much stronger.
So it's like when you take cornstarch in water and you can walk across it, do stuff.
Well, that's
It's non-Newtonian fluids. It's sort of like, that's a good metaphor for it, yes. But it's for a totally different reason. But it's a good metaphor for it, yes. The big pools of cornstarch, where you can, if you move quickly, you can run across it.
Yeah.
It's a metaphor for how spiders stay on top of water. Totally different reasons. So, hydrogen bonds always involve a hydrogen and something else. Usually an oxygen or a nitrogen or sometimes a fluorine. But in biological molecules, it's nitrogen and oxygen.
the first honey I did something that should get me jailed to the kids, or the book on which it was based. The young boy got trapped inside of a water droplet.
For Honey, I Shrunk the Kids?
Yeah,
Yeah.
that or the book it was based on.
Okay.
And they had to figure out how to pierce
Pierce,
the
yeah.
surface tension. Yeah.
Tiny little bit of soap. That's all it would take.
I think they had to use something physical.
Yeah, like a nail, something really sharp, yes. That would also sort of do it, but also sort of not, because if you push on the surface tension, all that's going to do is just create a new surface. Yeah, so it's just the water would bend around it, but the surface tension never really breaks. So it works for a story, but the science behind that actually breaks down.
The kid would drown first before they let him out if they're that small.
Right, but he would. But the other problem is if he's really that small, then he wouldn't actually drown, he would suffocate.
Yep.
Because when he opens his mouth, the tension of the water would be so high that it wouldn't actually enter his mouth. It would,
Take a needle and a water droplet. Yes, it'll deform, but then it'll eventually pierce it.
But then it forms a new surface tension right at the border where it's holding on to the needle. Unless the needle is nonpolar, at which point it'll pierce it immediately and then the water never touches it. But the droplet itself, if you touch that droplet with a needle, the droplet won't go. But try this.
But it gives him a path out. He can get, if you get the needle.
Right. No. Neater trick. Try that little drop of water, take your little needle, dip it in just a little bit of dish soap,
Yeah.
and then just touch the very top. Don't even try and pierce it, just touch it and watch that drop of water. Why? Because soap disrupts hydrogen bonds.
Put a little bit of alcohol do that as well, since it's invincible.
No, I don't think so. I think it'd have to be a non-polar substance.
Okay.
I don't think we can really say more Honey, I Shrunk the Kids, a common thing, so.
Right. What's a nice reference? Bug's Life, Honey, I Shrunk the Kids. This is why you stayed after class. Dispersion forces are neat. They're very, very weak interactions caused by temporary dipoles. Because here's the thing. When we're talking, and we're not really going to get any deeper than this, and I wish that we could, but it would take a much higher level chemistry course. But electrons aren't really things that have specific places. When we talk about understanding the shape of atoms, we are conceptualizing them in a metaphor that works great at really basic levels. But when you start getting into quantum stuff, you start talking about electron potential and electron density and all sorts of things that are really only represented by math. And so, because of that math, it means that that electron density can shift around in the same way that the surface of water can shift around. And so even in an atom that is otherwise perfectly neutral, sometimes, for really brief femtoseconds, that electron density will happen to be more on one side than the other, creating a very brief temporary dipole where one side of the atom is a little negative and the other side of the atom is a little positive. And so these dispersion forces are very weak attractions from temporary dipoles, but they are what allow for nonpolar molecules to form liquids and solids, to have weak attractive forces from each other where they're interacting with each other because of the way that they're pushing on everybody's electron density. But it's temporary. And why does all this matter? Because the melting point of a substance is dependent upon the attractive forces that keep it together. The reason that things are solid at room temperature is because the attractive forces between the atoms of that substance are strong enough to hold it in a rigid shape. So the more attractive forces we have, the more likely we are to be a solid at room temperature. The less attractive forces we have, the more likely we are to be a liquid at room temperature. Go even lower than that, and we might even be a gas at room temperature. Because the melting point of these substances is dependent on how strongly they are attracted to each other. So stronger attractive forces, like hydrogen bonding and ionic bonding, results in extremely strong lattice crystal structures. This is why water is less dense at 0 than it is at 4. Because as water freezes, it has to form a crystal structure, so that all of those negative and positive poles are pointed at each other. When it's a liquid, they can shift around each other and form and break and form and break and be just a liquid. But as ice, they've got to be... And that means the density is just a little bit lower, which is why ice floats. Ionic bonds between magnesium and fluoride has a melting point of 1,248 degrees C. These guys down here, the only thing that holds them together between molecules is dispersion forces, because they're nonpolar. So what form do these guys have at room temperature?
Gas.
Gas. Hydrogen bonding, melting point 0. Hydrogen bonding is strong enough to hold it together, so instead of being a gas at room temperature, it's a liquid at room temperature. Really, really strong ionic bonds, it's not even a liquid at room temperature, it's a solid. Ionic bonding and covalent bonding are strong. Hydrogen bonding, then dipole interactions, because that's just non-specific hydrogen bonding, right? And then dispersion forces in order of strength, so weakest down at the bottom, strongest at the top. And that's it.
Okay, just making sure, hydrogen and dipole are both liquid at room temp?
No, well, hydrogen is liquid at room temp, but specifically water is liquid at room temperature, and ammonium is liquid at room temperature as well, because it melts at -78. That's also hydrogen bonding. Dipole interactions, hydrogen iodide, hydrogen bromide, hydrogen chloride, they melt to be liquids, but when we get down to dispersions, and some of these are even gases, you get down to these dispersion forces alone, and you're dealing with gases.
So I guess the low, okay, so it could vary with dipole with gas.
Right, because
and
a
liquid.
dipole is just any interaction that's from a dipole, and dipoles are dependent upon what you're talking about, right?
Mm-hmm.
So hydrogen bonds are a specific type of bond where we know what one half of that bond is, hydrogen. But the strength of those hydrogen bonds can still vary, because the electronegativity between oxygen and hydrogen is different than between fluorine and hydrogen, right? And so, but it's still just a special type of dipole that we call hydrogen bonds, which tend to be strong. But you can have dipoles that are strong, you can have dipoles that are really, really weak. And so, the weaker the attraction, the weaker the interaction, the more likely it is to be a liquid or even maybe a gas. I am just a klutz today. It's because we're here too late.
Yeah.
So anyway, that's all of chapter 6. Only an extra half hour. If we hadn't gotten stuck on Honey, I Shrunk the Kids, maybe it would have been a...
15 minutes.
But yes,
You are the Richard Ford.
there we go.
I will communicate.
And I will send an email out letting everyone know that we voted as a class and everybody agreed chapter 6 is going to be on it. So, I'm really mildly nervous. What's
When is
this?
this video being posted? Are all the videos being posted?
I think they're all.
Ask him.
Yeah.
Sir?
Sir, wow.
I don't know your name, so I say.
Yes,
so.
student?
Now, when is all of this being posted?
I am working on it right now.
Okay.
I'm gonna go home, I'm gonna pull the external hard drive from my computer, I'm gonna go to church, where we have 12 megabits upload.
Are some
Yeah.
already uploaded or not?
2 portions of lecture 2 are uploaded. And right now I'm making those raw files that, it gets so big and then it moves to the next one, moves to the next one. Doesn't have the, the nice placard at the front and whatnot. And our nonsense after class cutoff. I'm making those available until I render, nice ones. Which I got the first one done. It's stalled uploading.
What is it called?
Oh, if you go on D2L to the discussions, in that tips and tricks and whatever section, I just posted,
Just
yeah.
happened to do something.
It's a playlist link, and as I get the refined videos available, I'll take the raw ones off.
Okay.
So it'll just end up just being lecture 1, lecture 2, lecture 3. I think it's fine. I have to give you one of these, right?
Probably. I still think I'm gonna need to get an email from them to validate it, but yeah.
Yeah, I don't think I'm actually, I won't be successful, but I might be able to take it there and have the quiet room.
I'm gonna try and.
There's rooms in the library too,
Oh, I like that, because I could,
and then you don't even have to worry about that, unless you just want the extended time. But
Yeah.
the library, you can,
Which one do I
nobody's
give you?
there in the summer.
doesn't say. Oh,
Should say on the
test
bottom.
mic testing center, yellow instructor.
It's like, that's where I
usually go to the library.
Thank you.
unless they specifically want it
What's that?
proctored into the testing center.
Sure, what's up?
And none of these are proctored.
Yo copy?
Thank you.
If this Cavanova went home with me,
Then the people who teach music there would be very mad.
but I'm in the middle of repairing a P200 and that's a P105. Well, I could use that one.
I saw nothing. Until someone asks.
So one of the questions, when we went to school or multiple choice, I was like giving like the working, then find out the answer. Did you see that? Or
No.
did you just want the answer? Final answer?
What I need in the solution is just the final answer.
Oh, well.
Right, because the box itself has a limited amount of space.
Yeah, I went typing everything, then finally and everything. So that failed me. Oh, you're gonna go in and look that's what I did.
Send me an email and mention it, and I'll go look. If it's there, then if it's saved at all, then I can go back and double check. If it only kept